So yesterday we started by as a sort of warm-up for understanding higher spin theories. We looked at the SL2R times SL2R formulation of ordinary gravity. So in the case of ordinary gravity, we found that we could reformulate the theory in terms of two SL2R Chern-Simons theories. So the action was very simple, and the equations of motion were just that the field strength associated with each of these gauge fields is zero. So at first sight it might seem as if the theory is empty, that everything is pure gauge, but we know that there are non-trivial solutions like AdS, so what you really need to physically impose are asymptotically AdS solutions, and there was a one function worth family of this. So we saw that we could put things into a gauge where A was equal to some B inverse A of Z B plus B inverse BB, and similarly for the other variables, and this A of Z which is a holomorphic function. So it was L1 plus 2 pi over the level k hat times an arbitrary function L minus 1 dz. So all the asymptotically AdS3 solutions were parameterized by one function L of Z, so I mentioned also that for the particular solutions where L is a constant correspond to the BTZ black holes, and of course the way to verify these statements is to put this back into this, so B was e to the rho L0, so use this and find A, and similarly A tilde. You know what the field bind is. It's just essentially the difference between A and A tilde, and from the field bind you know how to compute the metric. So you obtain the metric. You find is that these are all solutions in a Pfefferman-Graham-like coordinate, where rho is the radial coordinate, and these are sort of the functions that parameterize the components of the metric. You get back a global AdS for the particular value I mentioned, as well as all the BTZ black hole metrics. Moreover, in this Pfefferman-Graham-like formulation, you can also convince yourself, if you're familiar with that formulation, that this L of Z is the expectation value of the stress tensor, because in the Pfefferman-Graham-like expansion, or in general in AdS CFT, we know that when we expand the boundary value of the metric, the term which plays the role of the expectation value of the corresponding operator is the normalizable mode, and the coefficient of that is exactly this L of Z. So you can read off the expectation value of the holomorphic and anti-holomorphic components of the stress tensor from this. But if you want to function purely within the Chern-Simons formulation, then the exercise that I gave yesterday shows you how you convince yourself that L of Z behaves like a stress tensor, because we saw that the residual transformations that preserve this form of the metric act on, basically they change L of Z to in exactly the same way as conformal transformations do. So there was a residual set of large gauge transformations which act on this connection and generate the conformal transformations at infinity. So that was what we learned about the SL2R metrics and the SL2R formulation of gravity. And I also mentioned how the thermodynamics of the BTZ black holes can be obtained in this formulation by looking at the holonomies, in particular the holonomy along the time circle, which is contractible, is minus of the identity, tells you, gives you exactly the relation that you would normally have gotten from some Gibbons-Hawking-like argument. So those were things we saw about 3D gravity. So, and then at the end, of course, I rushed into telling you the generalization to SLNR. Let me revisit that, but let me start by just focusing on SL3R. So the claim that this SL3R times SL3R, Chern-Simons theory, is a theory of massless of S equal to 2 and 3 gauge fields in interacting gauge fields in AdS3. So so that's the claim. Let's look at it a little bit more. So for this, so this claim is true when the SL2R. So the adjoint representation of SL3R, the adjoint representation is 3 by 3 matrix, and it's traceless. So there are 8 independent generators. If you embed the SL2R of gravity inside this SL3, so in general there are a couple of inequivalent ways in which you can have an SL2R subgroup of an SL3, the one which corresponds to the spin 2 and the spin 3 gauge fields is the one in which, if you decompose the adjoint representation of SL3 in terms of SL2 representations, you get this 3 plus 5, where these are SL2. So this is adjoint of SL3. And this is the adjoint of SL2 of the usual 3-dimensional representation. And this is sort of second rank traceless, symmetric traceless representation. So if you embed the SL2 in such a way that this 8 decomposes into the 3 plus 5, then that is a realization of that I claim is the realization of S equal to 2 plus 3. And here I've written down, I mean, just so that you see how concrete it is, an explicit basis of SL3, which realizes that embedding. It's very similar to what you know from angular momentum, because the SO2, 1 is very much like SO3. You see the adjoint, the J0 with spin 1, 0, minus 1, and so on, and then the raising and lowering operators, and then there are additional the second rank tensors. So this is in fact what I was saying yesterday in equations when I said you think of these as the JAs and these sort of JA, JB, symmetric traceless. So you can so this is a different basis from that, but they are related. So you can this is you can re-express these in terms of minus 1, and you can re-express this in terms of the W plus minus 2 plus minus 1, 0. So they are just slightly different bases, but it's like again in angular momentum, you can write the spherical harmonics in terms of traceless tensors, the spin, the j equal to 2 harmonics, spherical harmonics. So it's this is just a concrete embedding of SL2 in SL3. If we understand that group theory, let's see what the dynamical content is of this SL3R times SL3R Chern-Simons theory. So we have again two gauge fields. We can always rewrite them as omega plus E over L and omega minus E over L. But now these are both, so this is just a parameterization. I'm always free to do that, or define omega as the sum and E as the difference. But now each of these omegas and E's, they are of course one forms, but you can also write them as EA, JA. And yesterday I used this notation TAB. You could so the general gauge field you expand in terms of these generators. I've tried to write here in this form rather than in terms of this basis, just because this is easier to write down. But you can also equivalently think of it as expansion in L0, L plus minus 1 and W and the W. So you can, and similarly for omega. So both of these have pieces which are SL2R pieces, and then the adjoint piece of SL2R, and then a symmetric traceless part of these omega of this TAB. So that these are the new fields. So in terms of SL2 representations, in addition to the field binds and the spin connections, we have these two additional sets of fields. And let's understand what they might be. So I'm rubbing this out. So the E mu AB, you see, has 3 indices. So I now have put explicitly the mu index because these were all one form. So I had here suppressed the mu index. But so if I have, so E was, so EA was essentially this. And similarly for omega AB. So these are both symmetric. So and this because it carries two tangent space indices here. You can, at least in a background of AdS, you can imagine a field phi mu nu lambda in which you consider E mu AB times the background field binds for AdS. So these are the background values of the gauge connection. So they are essentially they are the particular field binds that we wrote down here as some combination of L1 and L minus 1s. So you can do this and symmetrize in mu nu lambda. This object here, I won't show it here, but one can sort of show that the quadratic. Well, okay. At this stage, let me not talk of the equations of motion. So you have this field, but it also has a gauge transformation acting on it, because these were gauge fields. If you look at the gauge transformations. There's a gauge parameter lambda, which also has a similar expansion, lambda A, JA, plus some lambda AB, DAB. So you have a gauge, a new gauge parameter, lambda AB. This was the same thing essentially as what we had earlier. These are SL2R gauge transformations, so you can view them as the usual local Lorentz rotations. They in fact act by local Lorentz rotations on both the E as well as the EAB. So this part is just the transformation of spin 2 and spin 3 fields under diffeomorphism. But you have an additional gauge parameter lambda AB, and that also you can trade for object, which we can call lambda mu nu again, and it's a symmetric parameter. So you see that this object is a new gauge parameter which has two indices, so it's a sort of a rank 2 symmetric gauge parameter, and the gauge transformation that you have, the usual Chern-Simons gauge transformation, translate it into this, you find that this has a linearized transformation. So just at the linearized level, that means about the AdS background, it's essentially like this. So this is the statement that this three-symmetric tensor behaves as a gauge field with this new gauge parameter. So this is an additional gauge invariance that we have, and this generalizes, of course, the usual diffeomorphism invariance, which we also have, was G mu nu plus del mu some lambda nu. So we have this infinitesimal diffeomorphisms as well as the new spin 3 gauge transformations. So that it tells you that we are that this SL3R theory is at least SL3R gauge fields have the gauge symmetries of spin 2 and spin 3, and sorry, E bar, yeah, this is the background value. E in general is the general field bind. The metric may in general not be AdS, but I'm saying if you expand around AdS, taking this as the background value of the field bind, you can get a rank 3 tensor in AdS, and that rank 3 tensor has this gauge transformation. So it's a linearized gauge transformation because we are keeping the background fixed, so it's just the linearized transformation around AdS. Yeah. Sorry, I should have 1 second. Sorry, this would be the covariant derivative around AdS, and similarly. Yeah, go ahead. Sorry, I can't hear you. E? Yeah. 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 So there are generalized higher connections as well. So the omega AB also will lead to some rank 3 object, which is a new connection. but we'll see it's the analog of the spin connection in for diffeomorphisms. In the ordinary frame formulation of gravity, as we saw yesterday, the spin connection is determined in terms of the field bind by the torsion-free condition. So when I write down the equations of motion, there will be a similar quantity which will, in general, express this higher omega in terms of the other fields, namely the metric field and the spin-free field. So you can go to a purely metric-like formulation in which your only variables are this and this, just like one can do in gravity. But it's more, the equations are much simpler in terms of this combined set of fields, including this additional generalized, it's called the generalized spin connection. Yeah. So I didn't write down the transformation of G mu nu under this lambda, under this transformation, but indeed G mu nu also transforms under this. I didn't write down the full set of transformations. So of course, phi mu nu lambda, so these are under the diffeomorphisms. Phi mu nu lambda will transform as a spin-3 field does under this, this diffeomorphism. And similarly, G mu nu will also have a more complicated transformation law under this additional spin-2 gauge transformation. And everything is fixed by this, you know how the gauge transformations act on your Chern-Simons gauge fields. You can just sit and work through, and it looks a lot messier in this metric formulation. It's much nicer in the Chern-Simons formulation. But you can see already that under, supposing you had only this gauge transformation, you didn't have this, you will have the E, which is the part of the field bind, which is under the SL2, will also transform when you make this gauge transformation, simply because the commutation relations of these are non-trivial. So there will be non-trivial action on the gauge, on the field bind from the spin-2 gauge transformations. So there will be a more complicated form, and that's what is part of the interesting as well as unusual features of the Vasiliev theory, that you have a larger gauge symmetry than diffeomorphism on which acts on the metric. So ordinary diffeomorphism invariant quantities in this setup are not necessarily gauge invariant under the full set of gauge transformations. And which is why the notion of horizon, which we in diffeomorphism invariant theory is a gauge invariant notion, is not necessarily a gauge invariant notion in this theory, because the light cone structures need not be, I mean, what you mean, how you define the horizon is not necessarily going to be preserved under such a transformation. So, yeah, so.
Sorry, Rajesh, can I just? So at the linearized level, the spin-2 and spin-3 fields don't mix under a gauge transformation, is it?
Yeah, at the linearized level, they don't mix, but yeah, the nonlinear level, they'll mix.
Thank you.
Which is SL2R, so that we can get the traditional gravity wave. But this AdS3 will also have a conformal symmetry. In this setup, will that be evident?
Yeah, I will talk about that in a moment, how the conformal symmetry, yeah, I'll answer that question. So this is the general form of the solutions, and yesterday I wrote down for L of Z, I think it was something like minus sort of some k hat over L times something, some number, essentially. That was essentially the background value for AdS3, and so this is gives you a background background gauge field, which by these expressions fixes a background field bind, and so that particular background field bind is what I'm calling E bar. Okay, any other questions? Okay, so one can do so now one can, so far I just talked about this SL3R gauge field, and under a conventional SL3R gauge transformation, how the gauge fields behave, which can be viewed in this metric language as some linearized spin 2 and spin 3 gauge transformations. But now let me talk about the action. So we once again take the action to be the Chern-Simons action. So we take once again the same thing as I wrote down yesterday, but now with SL3 gauge fields. And therefore the equations of motion are once again the flat connections, but now the field strengths are with respect to SL3. So in addition, so these will have, so okay, so maybe I should, so you have things both so you have not just the SL2R field strengths, but also these components of the field strength also vanishing. So these would give you essentially the torsion-like equations that we had, but with some additional terms, because the A from the quadratic pieces, the A wedge A pieces, you will get pieces involving the spin 2 field also appearing over here. So Einstein's equation will have a source term from the spin 3 field. So remember, f of A was essentially dA plus A wedge A. So even though we look at the SL2R component of this, there will be pieces from this commutation relation. You'll have pieces which involve two spin 2 gauge fields, and that will appear, that's, if you wish, the stress tensor of the spin 3 gauge field, and that will of the spin 3 gauge field, that will appear as a source term in the Einstein equations. Similarly, the torsion equations will also have pieces involving both the spin 2 and spin 3. So this will give you, so in principle, you can use these equations to the torsion conditions to eliminate the omega A and the omega AB, the spin connection in terms of EA and EAB. Then the other two equations will be the dynamic for these two gauge fields, or if you wish, these two, so the remaining equations are the dynamical equations for the EA and EAB once you've eliminated omega, and they are complicated nonlinear equations. So they are generalizations of the Einstein equation. It's very difficult to write them in general, in sort of a closed form, but at the linearized level, these equations are the wave equations for phi mu nu lambda and g mu nu around an AdS background. So many years ago, Fronsdal had written down generalizing the linearized Einstein equations, equations for a spin 3 gauge field subject to this kind of linearized gauge transformation, and these wave equations, these Fronsdal equations. So these are called the Fronsdal wave equations. They are not very difficult to write down. They are. I just don't have the time to explicitly write them down for you, but they are basically generalizations of the Einstein linearized Einstein equations so linear wave equations, and you get them. You can get them from by this procedure that I just outlined. So that once again tells you that you have the content of a spin 3 gauge field, and these equations give you the nonlinear version of these linearized equations, which was the problem that many people, that Fradkin and Vasiliev and so on set out to solve, to find nonlinear equations generalizing the linearized wave equations for higher spin gauge fields. And in 3 dimensions, this is gives a solution of that problem. Okay, so any questions? Yeah.
What would happen? Chanceable theory looks pretty unique.
Yeah, so it gives you very specific diffeomorphism invariance. So diffeomorphism invariance will give you a general class of terms for the spin 3 gauge field interacting with the spin 2. But you want not just the diffeomorphism invariance, you want the higher spin, the spin 3 gauge invariance also. And that is what is going to uniquely fix those coefficients to a particular combination, which is what the Chern-Simons theory gives you. So if you could do this elimination here and write things in terms of EA and EAB, and in fact write in terms of phi mu nu lambda and g mu nu at a nonlinear level, you would indeed get a complicated equation of motion involving, of course, diffeomorphism invariant theories, but coming in particular coefficients such that they respect the nonlinear spin 3 gauge transformations as well. So that's what is sort of uniquely fixing the structure. Yeah, so maybe later I will talk about the coupling of matter, but indeed you can couple matter to this, at least scalar fields and fermion fields can be coupled, and there's a general way of doing it. There's a sort of covariant coupling that you can do. I might say at least at the linearized level something about that later. Okay, so but let me forget now about this frame-like picture, this metric-like picture where we write in terms of these metric variables. The frame variables are in some sense, the simpler ones. As you see, the equations and everything are much simpler in terms of this frame language. In fact, at the fully nonlinear level, no one has even written down the fully nonlinear, because to eliminate these at the nonlinear level is not easy. These are equations which are not easy to eliminate omega and omega AB and write in terms of EA and EB and write the fully nonlinear equations. People have done it sort of few terms, but not in general. So let me leave aside this form of the vectors and talk only about this in this frame language, this connection language. So we now look for the analog of the family of solutions that I wrote down for SL2. So we look for asymptotically AdS3 gauge fields. So unlike the spin 2 case where we knew what we meant by asymptotically AdS3, here it's a little less clear what you really mean by asymptotically AdS3. You know, okay. So what I will write down is a family of solutions which at least make sense as asymptotically AdS3 solutions, but it may be a restrictive class. There are likely to be solutions outside this class which are also which in some sense should be also viewed as asymptotically AdS3. This aspect is not completely understood yet because the meaning of what it means to say something is asymptotically AdS3 is not been completely specified, and I think that's an important thing to understand better. But at least okay. So the
I didn't understand that, Rajesh. There is no. There would be a notion of normalizable and non-normalizable solutions for these.
Yeah. So that's the sort of solutions that we'll write down. But there seem to be also solutions, especially when we turn on a chemical potential, and which I will talk about later. And when we turn on a chemical potential, then we are really turning on some non-normalizable modes. And that seems to also make sense, and in some way, okay, maybe I will address that when I talk about that particular case. But you're right, that using the sort of most conservative definition of turning on only normalizable modes, I'll write down a family of solutions right now. So that at least can be considered as the sort of simplest set of asymptotically AdS3 solutions. Yeah. So as Sandeep said, you have the spin 2 gauge fields and spin 3 gauge fields, and you want to turn on only those modes of these gauge fields which are normalizable, and the set of gauge connections which turn on the normalizable modes of the spin 2 and 3 gauge fields is the following. So we again can write down, it's again possible that one can show to write the parameterize it in this way with all the radial dependence sort of fixed. But now this A of Z takes on a form which generalizes what I wrote down earlier for spin 2. So we have, of course, we must have all the normalizable modes of the spin 2, so that part remains the same. But then we can have normalizable modes of the spin 3, which are conventionally normalized in this way, pi over times another function times this generator minus 2, if you wish, the highest weight generator of the spin 3 gauge field. So there are two functions now, this L of Z and W of Z, and similarly L bar of Z bar and W bar of Z bar for the A tilde or if you wish A bar. There's a very similar thing, exactly the same form as I wrote down yesterday for A bar, the anti-holomorphic piece with again two functions there. So you have this is the thing that we know is the expectation value of the stress tensor. But what is the meaning of this? So you have a new field whose expectation value is being parameterized by this. This would be, from the AdS CFT perspective, this would be the expectation value of the operator, which couples to that spin 3 gauge field. And there's a spin 3 gauge field with this gauge symmetry, the linearized level. It can couple to a spin 3 current, which must be conserved because of this gauge symmetry. The coupling for the coupling to respect this gauge invariance, that must be conserved. So it's natural to expect that W of Z represents the expectation value of a spin 3 current. So can be expected to represent the to be equal to the expectation value of a conserved spin 3 current let's see in what sense it's true. So we do the same. So if this exercise that I gave yesterday, which by the way is a very instructive exercise because it's one of the very simple ways to derive the Brown-Hainaut central charge. So I urge all of you to do this exercise. But if you did that exercise, you can similarly carry out the exercise for now the spin 3 version of this. So to see whether this expectation is borne out, you look at the gauge transformations lambda, which are of the form some B inverse lambda of ZB, which preserve this form of the form of A of Z. So in general, under a general gauge transformation, you will generate all the other modes as well, because lambda of Z is a general element of SL3. This is a general element of SL3. This is a general gauge transformation. So you will, by the way, sorry, I forgot the DZ over here. This is again the holomorphic piece. So you will generate terms under a general gauge transformation that will sort of take you out of this form. But if you ask what are the lambdas that preserve the form, you will find that they are parameterized by two functions. by two functions, epsilon of z, which was like the one that I wrote down yesterday, and then another one, say chi of z, two holomorphic functions, and basically, if you do this analogous exercise, you'll discover that you'll get some terms involving starting with epsilon of z, and another one starting with W2 and L1. So yesterday, the exercise, I wrote down a form for lambda in which you have epsilon, L1, and then there were terms L0, L minus 1, whose coefficients were expressed in terms of epsilon itself. In fact, that was by requiring that they preserve the form, you see that the coefficients are determined. Now, in this SL3 version of that calculation, you will discover that all the other terms involving all the other modes of SL3, L0, Ws, and so on, these are all fixed in terms of epsilon and chi. So there are two independent functions that parameterize the gauge transformations, which preserve the form of this A of z. And and if you look at how, so under epsilon of z, again, the L of z transforms. And then the second part of the exercise yesterday was to show that under such a gauge transformation, which preserves the form, how does the L part change? It will preserve the form, but L will go to L plus some delta L, and the delta L, that additional piece of delta L was exactly how a stress tensor transformed. So today, in today's version of the exercise, if you do it, you will find that under epsilon of z, L transforms as stress tensor should. But you also find that W transforms as a weight 3 conformal field. So its transformation will be basically how a weight 3 object transforms, namely as there'll be a factor of 3 epsilon times W3 and W of z, etc. So what you find is that you have a current which is weight 3 or a spin 3 object because it is holomorphic. So weight 3 means spin 3. And then under the remaining, under chi, you find an additional again, the L of z and W of z transform in a somewhat complicated way. But from that, you can read off the OPE of the L of z, just as under this conformal transformations, you read off how you can read off the stress tensor OPE with itself, and similarly the stress tensor OPE with this. From this, under the transformation of chi, you can read off the sort of WW OPE, and this you get a sort of a more complicated version of the stress so OPE, and that OPE is that of a current, I mean, it's a, so this OPE is in fact something that people knew earlier. It's that of a so-called W3 algebra in a CFT. So it's a CFT which has additional conserved currents, spin 3 currents, and in such theories with additional spin 3 conserved currents, the OPE of there's a definite algebra that is known, which is parameterized by the central charge, which so I should say this is W. This is what is called W3 algebra. So you find that indeed these can be viewed as expectation values of a spin 3 current, and moreover the spin 3 currents together with the spin 2 currents generate a non-trivial current algebra of the CFT, which is a known current algebra, which is called the algebra. Well, it used to be known to people in the 80s and 90s, so perhaps it's not something familiar to you right now, but you can find its explicit form in the literature, and it's a little complicated and daunting, but the procedure to obtain it is very straightforward, as I have outlined here for you, and hopefully at least the procedure should be clear. As I said, doing that exercise, yesterday's exercise, and generalizing it to today's will give you a sort of good hands-on feeling for this. Okay, so maybe I don't know whether I'll get to it today, but at least tomorrow I will give you an example of how to construct in a concrete conformal field theory some of these spin 3 currents explicitly, just like we construct the stress tensor explicitly in CFT. We can also construct these conserved spin 3 currents. So I'll get to tomorrow so that you get a little bit more concrete sense of this W algebra. Yeah.
How do I read out the boundary metric? I mean, the non-normal mode from here. Is it?
So you have to again put into the gauge field, and like I said, you know the piece of the gauge field which corresponds to the field bind, and you write down the metric and some Pfefferman-Graham-like form, and this form. It's better to just work with this. This is a gauge field. You don't want to, you make an arbitrary gauge transformation. So you basically write this lambda of z as some lambda naught L0, lambda naught of z L0 plus lambda 1 of z L1 plus so on, expand it in terms of all these generators. So in general, it's parameterized by 8 functions. But if you make this transformation by lambda of z on this A, by the usual gauge transformation rule, you will find that the new gauge field, A prime, will not necessarily be of this form. You want to preserve this form, namely you want it to be some L1 times some function times L minus 1 times some function times W minus 2. You'll have to make sure that the new gauge field, the coefficient of L1 is 1, the coefficient of L0 is 0, etc. That will give you conditions on these functions, and you will see that there are only parameterized by 2 independent functions which take this form. Rest are all determined, and under this transformation you get all the desired properties. So it's a very concrete thing. If you do it once, you'll get a good sense of what it means. But you can also write it out in the write out the form of the metric. Because these are actually W minus 2, you'll see these are in the metric, these subleading and so on. These don't contribute to their to the this thing metric, but you'll see that this is indeed the normalizable mode.
And
Am I running
no,
out of
no,
time?
no. If I can just ask, even though you're running out of time, if I can just ask a quick question. I guess in the spin 3 algebra also you have the analog of the Schwarzschian term.
Yes, there's
and
a central term, but it is with a coefficient which is fixed by the original central charge. So
Yeah.
it's proportional to the original central charge.
And all of that also one can understand just from a CFT kind of analysis.
Yes.
Thank you.
I mean, infinitesimally, that's what I mean. Infinitesimally, that's, I think, what he meant. There's a term which is C times the third derivative of epsilon. There's a similar term in this case, the infinitesimal. Yeah, I don't know whether the sort of the Schwarzian, yeah, that full thing under, we are only looking at infinitesimal. These are infinitesimal conformal transformations. Any other questions? Okay, so so this, by the way, I should say this the OPE that you find is that of what is called a classical W3 algebra, which basically means it's in the large C limit. The W algebra in general has some nonlinear terms which have funny factors of C in the denominator with some finite shifts. You don't see some of those finite shifts. So it's what is called the classical W3 algebra. So classical means large C. Large central charge, which is, of course, where we expect anyway our calculation to be valid because we are doing a semi-classical analysis. The Brown-Hanno central charge is large, namely the G Newton is small. Okay, so so the spin 3 example, if you have at least gotten some feeling for, I will very straightforwardly just mention generalizations to SLN without trying to dwell on the details. They are sort of they go over in a fairly straightforward way. So the SLNR generalization now the SLNR, once again, the SLNR, the adjoint of SLNR minus 1, you look at the SL2 embedding inside the SLNR. So in general, SL2 can be embedded in some huge number of inequivalent ways into SLNR, but the one which is relevant for us is the one in which the adjoint representation decomposes into the 3 plus 5 plus 7 all the way up to 2n minus 1. So you can view this as sort of, again, this is the adjoint of SL2 again, and this is the, so this is what I call JA. These are what I call JA, JB, symmetric traceless. Again, JA, JB, JC, symmetric traceless, etc., all the way up to rank n minus 1. So if you now talk of gauge fields again in the similar way, you have the generalized field bind E mu A, or let me just suppress the mu index. The E will be just again EA times the JA plus EAB, and this TAB. So I'll call these TAB, TABC, etc. So you'll have all the way up to some n minus 1, T A1 to A n minus 1. So you have, in addition to the field binds, you have all these fields. Once again, you can go to a metric-like formulation and write down mu1 to mu s is essentially E mu, mu to mu s minus. Okay. E mu1 and then A1 to AS minus 1, and then you basically trade off all these tangent space indices for the background. You symmetrize over these indices. So these are, again, the backgrounds. And so you see you get a spin, okay, I should have just put S. So, so you get a spin S field, symmetric spin S field, and the original gauge transformation. Once again, you have a gauge parameter lambda, which belongs to SLNR. So you get the same thing. So you have now gauge transformations, which so you can write each of these lambda mu1 to mu s minus 1 corresponding to each of these. So you get fields. You see this way, you have fields with this gauge transformation. Parameter will lead to a linearized gauge transformation, which is mu1 to mu s is identified with mu1 to mu s at the linearized level, plus a covariant derivative of the lambda so it's just putting various indices, and the values s go from now 2 all the way to n, because you have the maximum spin that you have is for an object which has n minus 1 upper index and 1 lower index, which you trade off for something with n lower indices. So you get up to maximal spin n. So you have exactly the same story as before at this linear level. You have these transformations, everything that I said about the linearized wave equations also hold. You get the Fronstal equations about AdS3. For these, you get now more complicated. Now you see you have gauge transformations for each of these. You have independent gauge transformations for each of these fields, the diffeomorphism being the first, but you get independent gauge parameters for each of these, and which correspond to each of these lambdas that you have. And in general, they just mix up all of these fields. So it's a huge gauge symmetry for n. Diffeomorphism is just a tiny part of the gauge symmetry of this SLN theory. And so you have all the same things as before for the gauge. This is kinematics, but we can look at the dynamics, namely the Chern-Simons action once again. You write down the same Chern-Simons action, but for SLN, you can write down a similar basis, etc. Again, fairly explicitly, you can write down a basis for these SLNR in terms of these various generators, and the flat connection. So the equations of motion for the Chern-Simons action are again the same f of a equal to 0, but now for all of these. So you get sort of A1, A2, A1, A3. So you get all these. And so there's a family of connections which are asymptotically AdS3. in which are parameterized exactly the same way with this, the radial dependence is fixed, and there's a holomorphic piece of the gauge field which now takes the form L1 minus some numeric, some normalization times Ws of Z, and now you have the spin S generator and minus S minus 1. So it goes from 2 to n. So now you get, again, n minus 1 independent functions, these Ws of Z, and these are the generators. So this calligraphic W is the function, and these are the generators, analogous generalizations of these. So you pick the sort of highest weight modes, the highest weight generators, and these functions are the normalizable modes of these gauge fields, and these are just some numbers, some normalization factors, so don't worry about that. So you can do the same thing. You find the asymptotic symmetry algebra by looking at the set of gauge transformations that preserve this form. Gauge transformations that preserve this form. Are parameterized by n minus 1 functions. Sort of epsilon S of Z, S equal to, again, 2 to n. And under these transformations, the Ws of Z transform as spin S currents. And because they are holomorphic, they are conserved. And that's what you might expect also from by viewing them as the expectation value of the corresponding operators. And moreover, they generate a closed algebra, closed but nonlinear algebra under the OPE. And this is what is called the classical Wn algebra. So it's again a generalization to something in a CFT which has conserved currents of spin all the way up to n from spin 2 always being the stress tensor, up to spin n. This algebra is called the Wn algebra, and you have it's a known algebra. Again, you get it at the classical level, the large C limit of this Wn algebra. Is there any question? I went through this very fast because it's just sort of transcription of the earlier statements, just to a general n. Yeah, I think we should stop there. Yeah, I think this is maybe a, yeah, otherwise I would have to talk about black hole solutions, and I think maybe I should just stop here. Yeah.